Okay, this is a practice lecture for object-oriented programming, and today's lecture is number 11. What you'll see in the notes is that lecture 11 and 12 are kind of just run together. What I'm going to do here is I'm just going to go through a load of different examples of design patterns and show you how to use them. I'll stop roughly halfway through for this lecture, and then I'll finish the rest of it off for the next one. Before we get on to design patterns, we're going to finish off looking at some functional features. We're going to look at the Streams API. So last time we looked at anonymous classes and lambdas and method references, and you'll see with the Streams API why that might be useful. So by the end of this lecture, I want you to have an idea about simple ways to use streams. Then we're going to look at this idea of design patterns, and I want you to know what a design pattern is. And there's this key principle called the open-close principle, which you should be able to remember. And then finally, I'm going to finish off with some example patterns today, and then that will go into the next lecture as well. So Java 8, I think it was, added stream support to collections, and the idea was that rather than having to use iteration to go over every element of the collection one at a time, say for like a for loop or a for each loop, you can instead turn your collection into a stream, and then you can filter and map your stream. Now, I'm going to show you some examples of this now, but in general, there's a sort of a pattern that you follow when you're using streams. So the first thing is you start with a collection, and then you call stream on it, so that creates the stream. Then you perform some series of element-wise operations, so maps or filters, and you can do as many of them as you like. So you can map and then map and then map, or you can map and filter and map, or however you want to do it. And then finally, you do some sort of aggregation at the end to get the result out of the stream again. So, for example, you might collect it back to a list, or you might sum all the elements, or something else. Streams can only be used once, right? So they're more like an iterator than they are a collection. So once you've created a stream, you can map and collect across it once, but then the stream has like been used after you've done that, and you can't use it again. Okay, let's have a look at some examples. I've written a college class here. Colleges have a name and a founding year, and then I've got a list here of all the colleges, and so I can get a list of them out of the from this static constructor method to give me a list of colleges. So let's say I wanted to make a list of names, and I was going to do it in the sort of traditional way, right? So I've got my list. Names is some sort of new kind of list. I'm going to say for each college in colleges, names.add college.getName. Okay, so that iterates through every element in colleges, adding each college's name to the list. So with the Streams API, I can do something slightly different. I can say stream names equals colleges.stream.map college.getName, and then collect the results up to a list. So you can see the pattern here. So first of all, I create the stream, then I do an element-wise operation on it. This time it's map, and then collect here says, please go through and collect all of the elements in my stream using this collector, which is the toList collector, which will then give me a list. You can see IntelliJ's got a good idea here. It's saying that I could use a method reference instead. So remember the method references from last time, the colon syntax. And the other thing that I can do, which is useful, is I can do a static import. So at the top here, you'll see that there's a new import statement, and it says import the static method Java utilstreams collectors toList into my program. So this means everywhere in my code I can now write toList, and Java will resolve that name against collectors. So you can use that quite a lot to make your code a bit more concise. If you know the reader of your code will understand where that's come from. Okay, so let's say instead we wanted a list of names, but we wanted them sorted alphabetically. So we can do that. So we say colleges.stream, and then we get the name again. And then this time we can say I would like it to be sorted, and I can collect that to a list again. Let's just do the same thing as last time. Okay, so now these are colleges' names which are sorted alphabetically. If I wanted to do a more complicated sort, I could sort by founding year. Now to do that, I'm going to need a comparator, which you should remember from last time. And what my comparator is a comparator on colleges, and it's going to sort them by age, or sort by founding year. And I can say comparators dot comparing college get founding year. So this just says give me a comparator, so a thing I can use to compare two colleges to see whether they're greater than or less than each other. And this is just a static factory method that I can use, which says call the get founding year method on college and then compare that in order to order the colleges. So this is called the key function. So it says, given this object, extract the key and then sort by that key. So the founding year is my key. This is going to sort them in ascending order, so the oldest college first. If I want them in descending order, then I can just say that I want a reversed comparator. Now I can say list string age ordered, and I can say colleges.stream. So now what I need to do is sort by my comparator, and then I want to map to get the year, get the name, and then I want to collect back to a list. So here I've got my colleges ordered by name, ordered by age. And again, the same pattern is here. Get the stream, do stuff to it. So here are my element-wise operations. Sorted is a different kind of thing, but you can stick that in there as well. This will sort and then do the next thing, and then here's collect. And here is a comparator. Remember those from last time, we're just using those to compare those objects. Here we use the natural ordering of strings, right? So strings are lexicographically ordered, so I could just use the natural ordering. Okay, let's do some other things. Let's list it by age. So I can say colleges.stream.map, and then I want to take my college and I want to do this year minus college.getFoundingYear, and then collect that back to a list. So that's the ages. Now, the next thing you might want to do is compute the average age. So I'll sort of finish this command off from the middle outwards. So I've got my stream. I'm going to map it like I did last time. And now what I'd like to do here is compute the average. But you see there's a thing here for count, so that will count the number of elements in the stream. But there's nothing in this list for computing the average. And the reason for that is it doesn't make sense to compute the average of an object, right? This map function, map here is on objects. It's mapping some object to another one. And what we really want to say is that actually we're working with ints or doubles or longs here, so we can then compute things on them. And so there are some options for that. So here's map to int. So this is now a stream of ints. So that's different to a stream of integers, remember. So a stream of ints is the unboxed versions. And because they're ints, I can do calculations on them. Like, for example, I can compute the average. Or I could say get the minimum, or I can count them as I can before. So the point here is that map takes works on objects, right? So it knows map here is expecting to take something of type college, because it knows that's what's in the stream, and it knows the output is going to be an object of some sort. Because we're producing an int here, it's going to be autobox and it's going to be an integer. So the type of this map function is college to integer, and then we collect into a list of integers. If you want to produce a map that goes to a primitive type, then you need to use these map2 functions, and then map2 knows that it takes a college and it will produce an int as the return type. Now, I haven't yet used the value from this. If you look at the return type, it's giving me an optional double. And the reason it's giving me an optional double is that there might not be any elements in the list, and so we'd have to decide what to do if the list was if there were no colleges in the list. What I'm going to do is I'm going to say or else throw, which means basically like abort the program at this point because something has gone wrong. So now here's my double average age. Okay. Now another thing we can do is we could produce a map, like a dictionary of names to founding year. So that's going to be a map from string to integer. Let's call it lookup. And the way we do that is we stream, and then rather than collecting to a list, we're going to collect to a map. Now, when you collect to a map, you have to tell it how to get the keys for the map and how to get the values for the map. So you need to give it 2 extra functions. So to get the key for the map, we're going to use the name of the college, and to get the values for the map, we're going to use the founding year. And that's all there is to it. Now I've got to look up a map which looks up all the elements in my college. All my elements in colleges, finds the colleges by name, and then stores a map for finding year. There are lots of other collectors you can use to do various different kinds of aggregation, and you can find lots of docs about them online or on Stack Overflow, and they're good ways of getting things back out of your stream again. Okay, so one of the provisos of using a stream is that you can only use it once. So it's quite bad style to like store a stream in a value, right? Because you have to remember now that you can only use this stream once, and once you've used it, you have to stop using it again. So I wouldn't do this. Because you'll lose track of whether you've used it or not. And the second one is that you have to be careful. Your map function should be stateless, right? They shouldn't have any side effects. So let me give you an example of that. Imagine I have like a, let's do it up here. So here's some int, right? And I'm going to say, what we're going to do is we're going to take the numbers. So remember I said there were different kinds of streams, of like streams of objects or streams of primitive types. This is a stream of primitive type integers, and I'm going to go from the range 0 to 1000 inclusively and exclusively. So that just gives me a stream going 0, 1, 2, 3 all the way up to 999. And then for each element in the stream, I'm going to say do 2 things. Update the value of last to be v, and then just return v. So this map function does nothing to the elements in the stream. It just returns them again. So it's like the identity function. But as a side effect, it keeps track of the last element that it actually looked at, and then stores it in this member variable up here. And then I'm going to just sort of like I'm going to add them up. So we're not really interested in the result here. What we're interested in is what happens in last, right? Because if we run this, then it should go through the stream one by one, and last should have the value 999 at the end of this program. So if I just say let's create an instance of it, right? And I'm going to run this code. Let me run it here. Then it prints 999. Okay, so that all seems good. But streams make no guarantee about the order that you're going to traverse the stream in. So one thing you can do, for example, is you can tell Java that it can execute your stream in parallel, right? And the thing that's important here is that the map function, the thing that I've asked it to map over, doesn't know that the stream is being used in parallel. That's like a previous call. But this function here is just going to be applied to each element, but now it's going to be applied in parallel rather than sequentially. So then your guarantees for ordering disappear, or well, you never had any guarantee for ordering, but actually your ordering disappears, and now we start getting different values with any luck. There you go. So there's 905, 405. So the things to remember is that the reason the stream abstraction is built like this is to allow different forms of traversal, so you don't have to go over all the elements in order. And as long as your map and your filter functions are stateless, then it doesn't matter which order they're run in, and so therefore your behavior won't change. But if you start doing things which are tricky and relying on the traversal order in your map or your for, then you start having a problem. This parallel call is relatively rarely used, but actually any kind of stream may or may not guarantee its traversal order when you're creating it, so you just don't rely on it. Okay, So that's a bit about streams. Now let's start talking about design patterns. So the idea of a design pattern is to have a general reusable solution to some sort of problem in software design. The idea was to say there are sort of common approaches to solving particular problems, and if we distill out what that common approach is, then the next time you come across a similar problem, then you can do the same thing. In my experience, actually, design patterns often help the other way round, in that when you're looking at a piece of code, it makes it easier to comprehend what the code is doing if you know about various kinds of design pattern, because the shapes are very similar. And when you're writing a program for yourself, rarely do you sit down at the beginning and think about all the design patterns you can use. Instead, what happens is you just sort of take a sensible approach and you go, aha, look, I've used one of these design patterns as I went along the way. The thing I'd like you to do with design patterns is think about the benefits of that particular design approach. So why that design approach is useful in terms of building a large software program. And when you're writing code, if you end up saying, oh look, this is almost like the so-and-so pattern, then think about why it isn't exactly like that pattern. Maybe you can improve your design a little bit. And when you're reading other people's code, then maybe you'll be able to recognize the way they're solving problems, and that'll make it easier to comprehend. But it's not a competition, right? One of the mistakes that people make with object-oriented programming is they go too far with this stuff. And so it's not a competition to see how many you can use in a single project. Just be sort of parsimonious with your choices. Design patterns are really good examples of something called the open-closed principle. The open-closed principle says that classes should be open for extension, but closed for modification. So what does that mean? Well, it means that I want to write my code once. I want to write my code in my class once, and then I want to leave it alone. But I would like other people to be able to modify its behavior of my class and use it in different ways and extend the software without having to change my implementation, because that means they then don't rely on how it works. So open for extension means that you can take my class and you can use it in lots of different ways, and you can add more functionality to what it does or to what your program does. But closed to modification means you do that without going into my class and altering the actual source code inside it. And as we go through these design patterns, I will try and try and explain to you examples of this as we see them. So here's the first pattern. So the first pattern is called the decorator. And the idea is to say, how can we add state or methods at runtime as we compose objects together? So one really good example of this is reading and writing files in Java. So I'm going to show you that now. So what I've got here is a readers class, and I've written a magic function here which downloads a book from the internet, from this source of books which are out of copyright, and stores it on disk. The only reason this is here is so that the demo works for you on your machines. If you clone the source code repo, there will be other ways of getting the book too. If you're interested in using networking from Java and all that sort of stuff, then there's much more of that in Further Java next year. This book, by the way, is Bram Stoker's Dracula, but it doesn't really matter. That's not important for the exercise. What is important is that we download it and we save it in a compressed file. So we zip the contents and we save it on disk. And then what we return is the file name of the book we've downloaded. So now I'm going to show you some stuff with I/O, and I'm also going to show you the decorator pattern, and also for free the adapter pattern. So let's start off, and I'm just going to read the contents of this file. Right. So I'm going to create an input stream, and I'm going to read the book. So some of this stuff you should recognize already. So firstly, you're seeing the substitution principle, because file input stream is a subclass of input stream, and so I can just assign this across everywhere. I can use an input stream, I can use a file input stream. So this input stream here, is for reading from this file. I've put it in a try with resources, which means when this block exits, then something will call close on this input stream to make sure I don't lose the resources. Now, input streams provide various sort of APIs on them. We're going to use this one, which reads some values into a byte array. So it's going to be a buffer. Let's say I have a buffer of 512 bytes. And I'm going to keep track of the number of bytes read. That's my counter. And I'm going to say while count equals is.read buffer. I'm going to explain what this line means now for you. So input stream.read, the contract of this method is that it will read as many bytes as it can and write them into buffer, and then it will return, and it will return the number of bytes that it read. So if it reads 10 bytes, then count will have 10. If there are more bytes available than the size of the buffer, then it will just read a buffer's worth and then it will return. So the maximum value I'll get from this is 512. And the trick is it's only reading the available bytes. So there could be more bytes to come in future. Say I was downloading off a network and only half the file is downloaded. I would read the first half, but there would still be more bytes for later, even if it hasn't done a complete read. And then the read function returns the value -1 if there was no data left, if it's the end of the file. Now I've wrapped all this up in a while loop because I want to say while you're reading, keep reading until you see the value -1. So you can see this bit here in brackets. This is a assignment, and remember that assignments are expressions and they return the value that was assigned. So this says read from the input stream into buffer and store the number of bytes read in count, and the return value of that expression is the number of bytes read in count. And so therefore, if that is -1, then we should exit the loop. Otherwise, we should carry on. But as a side effect inside this loop, count is now set to the number of bytes that we read. So I can do something like I is less than count. Okay, so this will print out all of the bytes in this book. There they go. I had to cast them to ints. Maybe I didn't have to cast them to ints. Okay. Okay. So this reads the bytes out of my buffer, so that's all very good. But actually, I had a compressed file, right? It was zipped. So rather than reading, well, what I want to really do is read the bytes and then decompress the file at the same time. So I can say that by decorating my input stream, my file input stream, with another input stream, which does decompression. So what's gone on here is that this gzip input stream, what it likes to do is it likes to read bytes from an input stream and then decompress that input stream, and it gives you another input stream from the outside. So what I've done is I've decorated the behavior of file input stream. So now rather than it just giving me the raw bytes that come out of the file on disk, it's going to give me the decompressed bytes that come out of the file on disk. So this is when I said runtime modification of behavior, what I've done here is this thing is still an input stream, so statically it's still an input stream, but now it's an input stream that decompresses a file as I read from it. So this is all fine, it will just print more numbers. There we go, lots more numbers. Now, what we'd like to do next is we'd like to turn those numbers into characters, so we can actually get like the text from the book. Now, Java has two ideas here. Input streams are for reading bytes, so for reading binary data, and then there's something called a reader, which is for dealing with character data. So what I can do here is I can create a reader from an input stream, and I'm going to tell my reader that the data that I'm reading is in a particular character set, so it knows how to convert one to the other. Right. So when I applied gzip input stream to file input stream, I decorated my input stream with another one. Now I have adapted my input stream to be a reader. So this is the adapter pattern. This is something which takes the input stream behavior and then alters it, adapts it so that it now behaves like a reader instead. It's not decorating it because the thing that I've got out is now a reader, not an input stream. So it's not dynamic. It's not runtime anymore. It's statically changed the type of the input stream to be a reader. It has adapted it from one to the other. So we've got two things going on here now. We've got one instance of the decorator pattern where I decorate the input stream, and one input of the adapter pattern where I adapt the input stream to be a reader instead. Now, readers don't work with bytes, they work with character arrays. And so I've got some sort of parse error in my program. We are. So now I can read arrays of characters from the book rather than arrays of bytes. Now you might say, what's the difference between bytes and characters? There's my arrays, there's my characters going past. Well, if you have a like non-ASCII character set, so you have like accents on characters and things like that, then characters can be bigger than a byte. And so if I was reading them from the if I was reading bytes from my input stream and just saying these are characters, then it would work some of the time for all of those characters which fit into one byte, and then it wouldn't work for the other ones. You just get garbage like through the file for half of the broken characters. Whereas what the input stream, what the reader is doing, is it's reading the bytes and it's saying, okay, I'm going to convert these into characters, assuming that they're encoded in this UTF-8 format on disk. So now I got characters back. Java's done all the hard work for me. But what I'd really like to do is read lines at a time rather than characters at a time. So I've got I can get these things into strings and do something meaningful with them. And so I can do that again by using a buffered reader. So now what I'm going to do is I'm going to decorate my input stream reader with another class, a buffered reader. And what buffered reader does is it lets me read to lines. So I can say while line equals is.readLine. So the contract of readLine is it will read a line from the file and it will return null if the file is finished and there are no more lines left. So what have we got here? We've got open the file and read it from disk, decorate the file so that we now are decompressing the data as well as reading from it, then adapt the input stream into a reader using the input stream reader, and then decorate that reader to add some more functionality, buffered reader functionality, which means I can now read lines from it rather than streams from it, rather than character arrays only from it. So now when I run this, it should print out the lines of my book. There we go. There's the text from my book. Okay, so this was the decorator pattern. Excuse the mess on this slide. Let me explain what this means in a sort of a UML form. So think about just this outer bit. So this thing here, we've got a reader and we've decorated it with buffered reader. So reader here is my interface at the top. So reader defines how to provides interfaces for reading characters from a file. And I have some concrete component, so a thing that gives me a reader in the first place. So in our example here, we had an input stream reader. That's a concrete component that gives me a reader from an input stream. Another thing you might have is a file reader, and a file reader gives you a reader from a file on disk. So if my file wasn't compressed, for example, I could just create a new file reader and just read, and then just use that directly. Then I took that concrete component, which extends reader, so this is of type reader, and then I decorated it with buffered reader. So what buffered reader does is it also implements reader, and you can see there's an arrow around here saying that buffered reader contains an instance of another reader. So that's the decoration. This buffered reader here contains an instance inside it of this input stream reader. So that's this arrow here, and then this decorator adds more behavior onto the object that we had. It's a function decorator. It's added on this read line behavior which we've wanted to make use of. Okay, so that's the decorator pattern. What you should be able to do with these things is you should be able to recognize one in code. So if you imagine in this case, if you had enough documentation available to you, then you would know what the different inheritance hierarchy is of these things, and so you'll be able to recognize that this thing is the same as that, which is taking then, which is then extending its behavior and changing its API and so on. I don't need you to memorize the standard library documentation for this hierarchy. That's something that you would just look up if you need to know it. But assuming that you did know these things, I would expect you to be able to recognize the instances of the decorator and the adapter here. And similarly, I would expect you to be able to parse this UML diagram and be able to explain why this is what this means in the context of the decorator pattern and why this is a decorator. Okay, so we're going to look at another pattern now. This is the singleton pattern. So the problem here is how can we ensure that only one instance of an object is created by developers using our code? So if, for example, we talked about try with resources, right, where you acquire some resources from the operating system and you need to make sure you give them back. What about if those resources are very expensive, or you're actually even only allowed one instance of them? So you might be, for example, connecting to a database over the network, and the database only allows one connection. And so you only ever want to create one of these database connection objects. Singleton pattern is a way to do that. So to demonstrate that, we're going to write a shopping cart, and we're going to do some credit card processing. So I'm going to need a class for items in my shopping cart. So we'll have items, will just have a name, and they'll have a cost. And then my shopping cart will contain a list of items. Import that class. Okay. And then let's make a constructor which just creates like an empty shopping cart. And then what I want to do is I want to be able to say that I'm going to purchase the items in my shopping cart. So I want to say, like, for each item in my shopping cart, do the purchase. Okay, so how am I going to do the purchase? Well, what I need is I need some sort of credit card processor. And this thing is super expensive to set up, so I'm just going to have like a static method which can debit the account and debit the amount, right? Let's do it this way. It's a credit card, so you don't owe me it now, you owe me sometime in the future. And there's going to be lots of sort of expensive stuff in here, which is like the connections to the credit card processor, and I might use like a static initializer to like set up connection and do all that sort of stuff, right? So I can set all these things up, and then down here I can say credit card processor, debit my account. I need an account number. Debit my account with the cost of the item. Okay, so this is a bit of a singleton, right? I can only ever have one of these credit card processors at any one time because it's a class and there's only ever one instance of the class. The problem with this approach is that I don't really have very much control over this thing, right? So Java will decide to load this class when it wants to. I'm using static fields, and so I'm having to make sure that I'm remembering that they're all going to be shared between all the instances. I've got static methods. The big problem here is that I can't use inheritance, right? So imagine I had another class here for debit card processing. Then I could have another method. Typo. And I could say and then I could say, well, this person has made a decision about whether they're using credit or not, and so I can say, if they're using credit, then use credit cards, else use the debit card. Okay, so you should be saying that this is not a very good approach because of all of the things we've looked at so far in the course, right? So first of all, we've made it very difficult to extend our class. If we want to add a new kind of credit card processor, then we're going to have to change shopping cart. So you remember I talked about open for extension and close for modification. This is wrong, right? Because if I want to extend my program to use another kind of money processing, say it's dealing with cash or money orders or something, then I have to actually go in and modify shopping cart. So I'm having to go in and modify the class. That's not very good for my design. So we know how to fix this, right? What we do is we use some sort of superclass, and then we use dynamic dispatch, right? So we can say we're going to have a sort of a processor, and what processors do is they know how to debit things. And then my credit card processor will implement this. And my debit card processor will implement this too. You'll notice I had to make these methods public. Remember, on an interface you get things for free, so you don't have to say public here because all methods on an interface are implicitly public. And if I wanted to, I could write override here, which would make sure that I didn't make a mistake and fail to override the method. So this is nicer, right? Because I can now, my shopping cart could contain the processor that I would like to use, and then I could just, here, I could say processor.debit, the account number and the amount. So item.getCost. Right, so this is better in the sense that I can now plug in different kinds of processors, but it's worse in the sense that I can no longer control the instantiation of those processors. So let me show you what that means. Let's say that I have a method here for creating shopping carts. So imagine what this does is looks up in the database my details and works out which account processor I want to use. And for the moment, let's just hard code it to return and some constructor parameters. Will it fix that for me? Yeah. Do that. So now I can say create me a new shopping cart with the account number 12345 and using a new credit card processor. So this is like a factory method for creating shopping carts, but the problem is now that every single time I create a new shopping cart, I get a new credit card processor, and I'd really like to make sure that there's only ever one of these things because they're really expensive to create. I have to pay the processing company for every single connection I make, for example. So what we can do about this is we can hide the constructor of the class and make it so that only we can make one. So let me just show you how this works, and then I'll explain it. So what's happened here is I've written a constructor for credit card processor, but I've made it private. So that means that anyone outside the class, for example here, is not allowed to call the constructor anymore because it's private. So this means that the only people inside the class can create instances of the class. Now, that might mean, you might think that means that you can never have an instance, but you can, because static methods are also inside the class. So this line here says, this line here says that create a static instance field called instance and initialize it with a new instance of credit card processor. And this is allowed to be called because although the constructor is private, this static initializer is inside the class, so that's allowed. And then whenever I want to get one of these things, I can no longer create one. Instead, what I have to do is call this getInstance method, which will return me the instance that I've stored in my constructor instead, in my static initializer instead. So now I would write here credit card processor.getInstance instead. So this is the singleton pattern. So what it's done is it's enforced that nobody outside of this class can create instances of this class. So I've controlled the life cycle, and then here I've provided access to that single instance that I'm going to allow to exist of that credit card processor. Now, when does this instance get created? Well, it gets created at the time the class is loaded. You remember the lecture we looked at on when class loading happens. And you might not want to do the work at the beginning of your program the first time the class is loaded. You might want to do it lazily, so you might want to do it at the point at which you actually need it. So you could do that. I'll do it on the debit card processor. You could start off, say, with an instance which is null, and then make the constructor null, make the constructor private, and then you could say if the instance is null, then create a new one, and then otherwise return the instance. So this is lazy initialization of the singleton, so it won't actually create an instance of this debit card processor until I actually need it, which is probably a good idea, given the viewpoint that it might be expensive to have one. This is not thread safe. Okay, so it's not safe to use something like this in a multi-threaded program. Again, more in further Java. But this gives you lazy instantiation of your credit card processor. So that's the singleton pattern. Now, that's not ideal either, because there might be other times that you want to change the kind of processor you're using, as well as when you're trying to change between credit cards and debit cards. And one particular instance of that is when you're testing your code. So when I test my shopping cart, I really don't want to have to make a decision at this point about, I don't want to actually have to make transactions on somebody's credit card in order to test my code, right? I'd like to use some sort of dummy credit card processor. And we have a problem here because shopping cart has got baked into it the idea that it's going to use this singleton instance of credit cards. Now, what we would like to do instead, and you saw an example of this in the Fibonacci task, is we'd like to inject these processors into the shopping cart so that it uses the right one. So one way you could do this is you could say that my shopping cart is going to take a map of strings to processors, right? So these are all the processors that are available to me, and then I'm going to load from the database the name of the processor that I'm supposed to use. So say credit, and then I look it up in the map, and then I can use that processing object. Then when I'm trying to use this thing for testing, so like in production mode, I can say shopping cart credit.create, and then I can give it a map of credit to credit card processor.get instance and debit instance. Excuse me a minute, I've got stuck. I've just got too many brackets. I've got too many brackets. Okay. So in production mode, I can create my shopping cart and pass it the production versions of credit card processor and debit card processor. If I wanted to have a test one, then I could say and then in testing mode, I can say just copy and paste this. I can inject the test version of this instead. And that test version doesn't even have to be a singleton. It can just work in a completely different, as just a standalone object. Now, people would now go further than this, and they would say, well, why are you writing code which basically wires your objects up together? Like, why am I having to explicitly say, when I'm running my program in this kind of mode, I need to create instances of all of these objects and pass them around, and when I'm running in test mode, I need to create different ones. Why can't that be done automatically? And the answer is it can, using something called a dependency injection framework. And that's beyond the scope of what I want to talk about in the course this year. So we're going to stop here, but let me just leave you with this idea that the singleton pattern is controversial because people argue about whether singletons are really the right thing that you want at all, and whether actually what you want is some other way of controlling the life cycle of an object, such as with a dependency injection framework. But if you do want a singleton, or you do read code where they've used them, then these are some example patterns that you can use. Remember that these are not thread safe, and so there's more complicated ways of doing this to try and make it safe in those examples. Things like dependency injection frameworks are not within the scope of this course, but trying to write code which is possible to test and satisfies this open-close principle is. So if you're using singletons, then think about how you're going to use them in the context of writing tests for your code and how you're going to push them around to make that work. So just before I finish here, let me show you the UML diagram for a singleton pattern. It's very, very simple. We have a static instance field, which is private, which contains the instance, and then we make the constructor not visible, and then we provide an instance method that provides the static instance that we've already created. Next time I'm going to finish off going through the rest of the design patterns and see where we get to.